I've started recording, so.
Can you go over the inverse functions? Like, I don't get that part.
Yeah, okay, so there are, first, let's talk about what an inverse is, because that'll make things make more sense. So if you have a function, like f of x, right, and you plug in a point x.
You're not sharing your screen.
Oh, shoot, sorry, forgot about that. Can you see my screen? Can you see it?
Yeah, no, I can.
Okay, so if you have a function and it has a point x, y, when you plug it in into inverse, let's say this is, actually, hold up, let me just, yeah. That point on the inverse is y, x, right? So they switch. So, um, so if, so when we derive, so let's say, now, like, just keep that in mind while I derive the, inverse function. So, uh, let's say g of x, there's two ways to do it. I'll show you the one that's easy and it'll probably make the most sense at first. So let's say g of x is f inverse of x, right? And we want g prime of x, right? So if we plug in f of x into both of these, then we get g of f of x is equal to x. And then if we take the derivative with respect to x, we get g prime of f of x times f prime of x is equal to 1. So g prime of f of x is equal to 1 over f prime of x. So, um, this term right here, the reason it's not g prime of x like we wanted to find is because of this property, right? So when we want to find g prime of 3, right, we need to find what x will get us 3, right? So what x can we plug in here to get the y that we can plug into the g of x that we desire? So, for example, do you have an example for inverse? Like a question that asks you to find the inverse, uh, or find the derivative.
F of x equals x squared if g equals f, or inverse f, and g prime of 4. What?
Okay,
Do you want me to send a picture?
just this, right? Is this it? G prime of 4 if g is,
Yes, yes.
okay. So g prime of 4, right? Well, we want f of x. If you look here, it's g prime of f of x, right? So we need f of x to equal 4, right? Whatever we plug in for the actual x. We need that to equal 4 to have a g prime of 4 and use this. Does that make sense?
Yeah.
Because we have g prime of f of x. So if we have a 4 in here, right, then um, then we need f of x to equal 4. So this is not the x we're plugging in. This is whatever point we want on the g of x. But clearly that's not x. That's actually y. So we need to find where y on our original function is 4, right? And that is at plus or minus 2. Is there a domain restriction? Like, is it, because there's two possible.
No.
Okay.
And you just got plus or minus 4 by making x squared equal 4, right?
Yeah, I got plus or minus 2. Do you think you could send me the question? Because it can't be both. It has to be one or the other.
Just two ways. So,
Yeah, if you could, is it possible for you to send the question? I think that would probably clear things up.
yeah. Yeah, it's in the chat.
Okay, let me check. Find g prime of 4 in 2 ways. Interesting, in 2 ways. I'm not sure if in 2 ways, because there are 2 answers to this, if that's what it's asking. If you have the answer key, do you have the answer key?
These are the problems we did in.
Oh, okay. Okay, let me think. 2 ways. I mean, there's only one way of doing this. The only thing I think 2 ways could be referring to is, oh, you know what it's referring to? Okay, so one way is doing it this way, right, with our derivation. Another way is just actually finding the inverse and doing it that way. So if we find the inverse, right? So if y is equal to x squared, we swap the x and the y. X is equal to y squared. So y is equal to plus or minus root x. That's our inverse, right? So there's still 2 answers. So I think our final answer is going to have 2 answers. I don't see a way around that. So
What's the question?
actually, it's in the chat. In the
Okay.
chat. Yeah.
But also, how'd you do on the Euro test?
42 out of 45.
What? And you were stressing?
Okay, so let's get back to this real quick. I just realized, what's the domain of this? What are the y's gonna be when you plug in x? They're all gonna be greater than 0, correct? Does that make sense? So if this is our inverse, it has to have the same domain. So we only actually need the positive part. So y is equal to root x. So that's our inverse, not this, because of the domain. So actually, scratch that. That makes... Actually, no, that should be right. Hold up.
Wait, you're saying that x has to be like. No. You're saying x has to be greater than 0, right?
X can be less than 0 too, but it's going to give us the same y.
I'm sorry.
But it's in a square root though. Yeah.
Yeah, that's why I'm thinking. That's why there's hold up. Just so x is here, y is over here. We can't plug in negative x's, which is interesting. Is it because shoot. Let me do something on the side real quick. Shoot, that's... Yeah, okay. It's because here. I'm trying to find the best way to explain this. The reason for it is because this x does not match with this x. These are not the same x. The x over here is what you plug in, right? So you plug in an x and you get an output, right? So here I plugged in plus or minus 2 and I got 4. The x on our inverse, it's if we're given a y. This is actually our x. Let me think about this real quick. 4. So oh, uh, shoot. I know there's... Okay, so x is equal to y squared. So Is Shrieker still there? Shrieker, do you
Yeah.
okay, so when you do the inverse, there's two possible answers. So I'm wondering how you narrow that down, or if you narrow it down. Because our original is y is
I'm
equal to x
thinking-
squared, so y has to equal plus or minus root x.
Yeah. Plus or minus root x. And then the other way is actually if you wait, I think if you think of it like
Yeah, okay. So I got it. So here, x is what you plug in, right? Here, this is actually your y, right? That's why this thing trips a lot of people up. This is our y, right? So this is our 4, right? So it's always positive. So the domains switch. So here y is always greater than 0. So the domain of our inverse is x is always greater than 0. Here the domain of our x is all real numbers, right? Here y can be all real numbers, right? Because of the plus or minus. So I think there's just two answers to this one, right? Shrieker, did you copy down this example, what he did? Because there has to be two answers.
yeah, I think so. The only thing, wait, just trying to read your break real quick.
So anyways, so one way to do this, the first way to do this is getting a little long-winded, but essentially the first way to do this is now that we have our inverse, we just take the derivative of our inverse, right? At so it's x to the 1/2, so it's plus or minus 1 over 2 root x, right? Because we get two slopes, because our inverse looks like this. So for every x value, we get two slopes, the plus and the minus. So what do we plug in into here? If we want g prime of 4, right, we don't plug in 4 into our x here, because in our inverse, right, we want if we want to plug in 4, so let me redo this. So if in g, if we plug in 4 and we get some number, right, in our f of x,
Yeah.
if we plug in that number, since of the switching, right, we get 4. So what number can we plug into our f of x to get 4? We can plug in plus or minus 2, right? Does that make sense? Is there any questions so far?
Yeah, and because of that switching, we won't directly put 4 into the the derivative.
Yeah.
Even though technically, if you think about it, isn't that still equal to g prime of x?
What is?
1 over 2 root x. Plus or minus 1 over 2 root x.
Yeah, this is g prime of x. But
And if we're trying to find g prime of 4,
then g prime of 4
then what's the reason?
but here's the thing, right? This x, these are not graphed on the same plane. And what I mean by that is, in our original function, right, y is equal to x squared, it looks like this, correct? This is our y, this is our x. Here, so x, y. And the reason that we plug in, sorry, wait, hold up. I see your question, why we don't just plug in 4 straight. And the reason for that is because g prime of 4, g is not a function of x. It's a function of y. Does that make sense? That's why it's important we know what we're taking the derivative of. It's a function of y, not x.
That makes sense. Yeah.
Because we plug in our y's and we
So
get an
so
x.
it's actually the g
So
prime
this
of
is
y.
actually y, yeah. But
I see.
that messes with our
Which
derivation.
means f prime of x is equal to 4.
Yeah. But if it's a function of y, that messes with our derivation, right? Because we're saying it's g of x here.
Yeah, exactly.
Why is f prime of x 4?
Why is f prime of x 4? F prime of x is 2x. Sorry, this is getting a bit
Yeah.
messy. Yeah. Yeah. So, and we want to find g prime of 4, right? So, all I'm saying is, in g, if g we plug in 4, that's our output on the f, because it's an inverse. So that means we need to plug in something on the f to get a 4, right? And that will be our g, that will be our 4 on the g, in the g function, right? Our inverse function.
Yeah, so wouldn't that I see. So I mean, saying that g prime of 4 means that means if you're saying it's a function like g prime of y, that would mean that f that would mean that 2x would be equal to 4, right? Because the derivative would be then equal to the y value. Well, oh, it would be y.
So if g of x is equal to f inverse of x, there's something, the thing I'm confused about is why we say it's a function of x in our derivation. Because
Yeah.
if we plug in 2 for x, right, f inverse of 2. Oh, okay. So, it's kind of difficult to explain this. It's still a function of x, but our f is actually a function of y. It's weird because we think it's f of x, right? And it should be. It actually should be. But the reason we say we we put g in terms of x and f in terms of y is just for the sake of making this derivation look simpler, right? Because it's in x's and that's what everyone's used to, so there's no questions about it. Does that make sense? So instead of having f of x and g of y, they're having f of y and g of x. Does that make sense in our derivation? They're still inverses, right? And again, these are just variables, so you can think about them in either way, right? Does that make sense? Is there any questions about that? Because I can explain it better if there's like questions. It's kind of hard to explain.
Complete the problem.
Yeah, I should probably complete the problem. Let me do that first. So that was all to say, right? If f is a function of y, right? Then if we plug in plus or minus 2 on our original function, right, f, then our inverse function, that will be the output. So and our output on our original function will be our input. So we know if we plug in, so we had 4 here, right? We want to plug in 4 into our g function. So we need to know, but but our derivative is in terms of x, right? And so we need to find the x value that that will give us 4 for g. So for f, that's plus or minus 2. So that's what we plug in into our derivative. Shoot, I can explain this better. Does it make sense what I've done so far? So once I plug in plus or minus 2, I get actually you only plug in positive 2 because the plus or minus is on the outside. So you get 1 over 2 root 2 plus or minus. I can explain this better. I can go over this better, and I think it'll make more sense. But is there any questions right now? That way I can start explaining by answering the question. It's probably just confusing, honestly. I can explain it better. I think I figured it out. So let's start at the derivation.
Where did you get 2?
Where did I get what?
2 root x, shouldn't it just be 2x?
Here, our derivative, is this what we're talking about?
Yeah.
Because our inverse is this. This isn't the function we want our inverse function. So I'm just taking the inverse. You know how to take the inverse, right? You just swap x and y and solve
Yeah.
for. So that's our function we're taking the derivative of. And the derivative of that.
Okay.
So let me explain from the start. This will make more sense. I got it. I get there's a lot of weird notation going on, and that's what's making this so confusing. So ignore the derivation that Shio is using right now just for a second. So let's say we have f of x and g of y, right? If we plug in a value into let's say we plug in x into f of x, right? We get x comma y, and then for g of x we get y comma x. Now, and that's if g of y is f inverse of x. But there's a mismatch. There's a mismatch here, right? You can't have a function of y by taking an inverse of the function in x, right? So we just say, okay, let's also make this a function of x, right? Right? And that doesn't actually change anything by making it a function of x, because we're still plugging in values, right? So even though this is technically y, we can call this x as well. It's not the same x. These are not the same x's, right? But that's why in our derivations we say g is a function of x, because it doesn't actually matter. So there was that whole derivation, right? And at the end there was g of f of x is equal to 1 over f prime of x, right? So if we want to find if f of x is equal to x squared, right? On the side, let me find the inverse. This is method 1. Right? On the side, let me just find the inverse. Y is equal to x squared. X is equal to y squared. Y is equal to root plus or minus root x. This y is not equal to this y, right? We're putting them on the same xy plane, but these are actually what are equal. Does that make sense? It's just notation. It's just so that we can consider them both functions of x. Does that make sense so far? Does it make sense? Okay. So, actually, you know what? I will keep that. So, if that's our inverse, right? And this is the y becomes the x and the x becomes the y in our inverse. If we want, so that means g of x, right? F inverse of x, which is equal to g of x, which is equal to plus or minus root x, right? If we want g of 4, right? We can't, this 4, it's really weird notation, but this 4 is referring to this x over here, right? Or actually, no, never mind. Ignore that. Yeah, it is. So g of 4, right? G of 4 is g of 4, right? So if I want g of 4, ignore the primes for now. If I want g of 4, what is that?
Plus or minus.
Yes, it's just plus or minus 2, right? Because we're just plugging in x's. But if we want the derivative, the way we set this up, right? We have an f of x in here, not an x, right? We don't have an x. So if we want g prime, and that should be a prime, of 4, we need to find f of x to equal 4. We need to find the f of x that equals 4, right? But ignoring all that, let's go back to method 1, right? So g prime of 4, let's just take the derivative of this. Do you know what the derivative of that is?
One over 2x.
And then there's a plus or minus out front, right? So we can just plug in 4 straight. Since we manually found the inverse in method 1, we can just plug it straight, 4 in straight. We don't have to worry about any of these value switching. It only matters because we found this basically shortcut, right? For when it's really hard to find the inverse. But for now, let's just plug in 4 straight and we get 1 over 2 root 2. Or not 2 root 2, 1 over 4. Plus or minus 1/4, right? That's g prime of 4. So that's method 1. Method 2 is the way he's going to want you to do it because you can't find the inverse so easily every time, right? And that's saying, okay, I want g prime of 4. I know that g prime of f of x is equal to 1 over f prime of x. So I need the f of x over here to equal 4, right? So what can I plug into x in the f of x to get 4? What can I plug in here to get 4?
Plus or minus.
Yeah, so plus or minus 2. So we need to plug in 2. So the x we're plugging in is not 4, it's plus or minus 2, right? So we need to find, so if f prime of x is 2x, right? 1 over f prime of x, so 1 over 2x. Let's just plug in plus or minus 2. Now we get plus or minus 1/4. They give us the same answer. So the only reason we have to think about the value switching is because we're finding this shortcut here. And so an easy way you can think of it, right, is if we want g prime of 4, right, that is some value, or that is some value if, let me, so g prime of 4 is if you plug in 4, you get some value, right? Well, f prime of x, let me put x here, right? You plug in x and you get 4, right? So you need to and because we have f of x in our shortcut, we need to figure this out instead of just plugging it straight because we can't always find the inverse. So does that make a little bit more sense? I can do another example without the derivation, or without the derivation, and I can show you how you would just do it like normally. I can do number 2.
That makes a lot of sense. Thank you.
Okay, let's do number 2 really quick. I'll do it just the second way. I'll do it this way. So I already have 2 written twice, but this is actual number 2. So if f of x is equal to sine x, right, and we want g prime of 1/2, that means since this is our inverse, right, we want, and we know that the derivative inverse is 1 over f prime of x. But since we're plugging in this to our inverse, we need to figure out what we need to plug in to get 1/2 on our original function, right? And our original function is f of x, is sine x. So what can we plug into sine x to get 1/2? We can plug in pi over 6, right? So that's what we actually plug in, right? So let me write it this way. Instead of so For G, there's a point 1/2 pi over 6, right? But for F, there's a point pi over 6 comma 1/2. These are related points, right? These are the inverse points. But since we have F, we're using F prime of X in our shortcut, we need to think about this. We can't just plug in straight what we see, right? In the problem. Because that's in terms of the G. That was the best explanation I think I can give. If there's questions about that. It's a bit confusing. I can like think about it as in like let's do this. This might help. So we have that's ln x, right? Actually, let me do these in different colors. That'll probably help. So that's ln x. Let's say that's our inverse. Right? And this is e to the x, and that's our original, right? For the point A, B, right? If we want to find, actually, let me do it here. Let's say we want to find, so if we have a point A, B, right? The point on our inverse will be BA, the corresponding point, right? So if we want to find the derivative of the inverse, the slope of the inverse, right? That's related to this point here. But see how the B and the A switch? So we need to think about that when we're taking the shortcut for our derivative of an inverse. Because again, we can't always easily find the inverse. Sometimes it's actually like really impossible to find the inverse. So since these are corresponding points, but they have different values, right? Because one's an inverse of the other, we need to think about that. Okay, I think that was the best explanation I could give. So does that make sense?
Yeah. Thank you.
Okay, so that's inverses. Is there anything else? Did you guys go over? I don't think you guys went over. Do you know how to do trig functions with the limit derivative? Like figuring out the derivative through the limit definition of the trig functions? Because that might be on your test. At least one of those is. At least one of the trig functions. Do you guys know how to do those?
Oh yeah, we did that in the beginning of the year.
Yeah, okay. Okay, just making sure. So that's one thing. And then you guys didn't learn did you guys learn how to find the area of a function? Like underneath a function? I don't think so.
No, not yet.
Okay, yeah. We learned this by semester 1, so we had a lot different stuff on our theory than you guys. So yeah, that should be. Is there any other specific questions you had? Because I'm pretty sure you guys got some sort of review. So
Quick question. So, there's this one question like from a worksheet that he gave about inverse, like with inverse on it, and it's asking to multiply like g of 0 times g prime of 0. But how would you find g of 0? Would that just be f prime of x?
that would be whatever. So if we want to find
Or then
g prime of 0, right? 0 is this point. It's not this point on the function, but pretend it's this point on the function, right? We need to find because we want to use this relation we found between g and f, right? Between our inverse and non-inverse. We want to find what value that corresponds to on our original. So in G, if we have 0 comma and our output is let's say a, right? On our original function, it's a comma 0. So we need to figure out what a is to use this I don't want to say formula, but like shortcut. Does that make sense?
yeah.
Does that answer the question? I'm not sure if it did, but that should at least put you on the right track to doing the problem.
Yeah, I'm gonna try it first and then see.
Okay. Is there any other questions? I'm gonna erase this real quick. And then actually, let me show you guys the derivation he shows for. So the way I showed the derivation was like using like functions, different notation. He uses the fraction notation, which I prefer anyways. So I forget exactly how to do it in fraction notation, but it's shoot. So if we if G is equal to, so if G of f of x, so we got to this point, right, is equal to x, right? Then, and we want d, it's honestly just a small difference. If we want dg dx, right, then we want to take, then we want, we know df dx, right? This is what we know. And we want that, right? Well, we can say df dx times, what can we multiply that by to get dg dx? We can apply that by, shoot, dg df, right? Right, and so dg df is equal to, shoot, I feel like I'm doing something wrong here. Is equal to 1, right? Because that's dg dx. We wanted to take the derivative of this, right? And that becomes this in fraction notation. So then dg df is equal to 1 over df dx. And the reason, and the quirk still shows up here, it's dg df, not dg dx, because just like how I was talking about with g of f of x, it's in terms of f. So we need to find what x will give us the right f of x needed. It's a similar thing, if that makes sense. So that should be everything about inverses. Let me look at, I think I brought my stuff with me. Let me see what I have in my theory. Oh, I have some always, sometimes, never. This is a whole portion. I don't know if you guys probably had a few on your theory pre-final, but I'll show you the ones that I got. So if a function, so always, sometimes, never. If a function has a relative maximum at x equals a, then f prime of a is equal to 0. Is that always, sometimes, or never?
Sometimes.
Why?
Because if you have like a linear, I mean a line, a horizontal line, the slope, the f prime of x would be 0.
Yeah, but this is asking, yes, but this is asking, okay, so it's asking if there is a function that has a relative max, right? Then does this always have to be true?
Well, I mean, it could be absolute. It could be an absolute.
Well, yeah, that's why I was trying to see. So basically, if there's a sharp point like this, right? Like let's say negative absolute value of x, y is equal to, right? That's a sharp point over here. Is that differentiable?
No.
No, but at the same time, it would be never, right? Or
It would
no, never mind.
be sometimes, because it's still a relative
It'd still
max.
be a quadratic, for example.
it's still a relative maximum because the definition of a relative maximum is that the point is greater than all the functions, or than all the points that lie next to it, that lie closely next to it, right? So this is greater than its neighbors still, right? But f prime of a in this case is 0, f prime of a does not exist. It could be a quadratic instead. Now this is true, right? But I just found something that was, so here it's true, here it's false because it's a relative maximum, but f prime of a is not equal to 0. It doesn't exist in this case. Here it is a relative maximum and f prime of a is 0. So it's sometimes. Does that make sense? That was a bit long-winded, but
Yeah.
okay. And then there's another one. This is where most people, I think this is the part where most people lose their points, if I remember from last year. I don't fully remember, but if f double prime of c is equal to 0, then c is the x value of a point of inflection. Always, sometimes, or never.
Is it always?
I want to see what other people think first. Does anyone have any? Does everyone else think it's always as well, or is there anyone that has a different answer? Okay, then let's Oh, did I think I saw someone unmute? Did they have a different?
I remember Shia saying it's sometimes, but I'm not
But
sure.
can you let's dissect this. Let's start from the beginning, right? So if we have a y double prime, right? This is just a one-dimensional graph, right? And c, right? That's 0, right? If it goes from positive to positive, is that a point of inflection? It hit 0, but if our y double prime is positive and then positive, is that a point of inflection?
No, right? It's for if it was if it was y prime line, then it would be.
It would still be a point of inflection. A 0 would be a point of inflection.
No, it wouldn't
See,
Wait,
actually.
no, the concavity has to like
Change,
go
yeah.
up and
Yeah,
down.
and this is yeah, exactly. The concavity has to change for it to be a point of inflection. That's the definition of a point of inflection. Since this is our y double
wait,
prime line.
hold on. Yeah, it would still be considered as a point of inflection.
No,
because
no,
It's,
no. It isn't. It's because it's y double prime. If this was y prime, and it went from positive
are you sure?
to positive,
Because
yes,
I
yes,
think
exactly.
on like some of my tests, on some of my
Here, I
tests,
have the answer key right here. It says it sometimes because, and this is a big sticking point that Mr. Shaw has. I don't know why he hasn't emphasized it to you yet, but this is not a point of inflection because concavity doesn't change. It has to inflect. It has to go from positive concavity like this to negative concavity like this. That's a point of inflection. Or it has to go from negative concavity like this to positive concavity. That's a point of inflection. If it goes from positive concavity to positive concavity, all that is goes like this, right? And then it stops, like literally for an instant. It stops. The slope stops increasing, and then it keeps on increasing. Like that's not a point of inflection.
Wait, no, the reason I initially thought that too, although actually after touching up tests and even like critical numbers tests, I think for some people he marked it off by not including that as a point of inflection. Um, and then I also like since I learned like after on the test I did include it as a point of inflection. I think I got that one right. So then
I mean, I don't know. Mr. Shao says this is not a point of inflection. He actually had to talk about this in class as well. It's not a point of inflection. You can talk with Mr. Shao yourself if you want to make sure. But I know
Yeah, no. So like if you had the Yeah. Okay. I see
Let me
what you're
see.
saying, but
Point.
if you had the graph go up and yeah.
So double prime is when the concavity changes, right?
Yes. So look,
Yes.
at this point, the second derivative of the underlying function will be 0, but positive on one side and negative on the other.
Yeah.
So it has to be positive to negative or negative to positive. It can't be positive to positive.
Yeah.
So that isn't a
Yeah.
point of inflection.
Yeah. Again, yeah.
So
Again, something that I
this
we
is
should look back
sometimes.
up.
Does that make sense? Let me keep explaining. Hold up 1 second. So that's one way to tell, right? And people sometimes get this confused with the y prime line, which is has a positive slope, then it hits 0, then it's a positive slope. If it was a y prime line, that is a point of inflection, because to go from positive to 0, it had to be concave down, and then to go from 0 back to positive, it had to be concave up. So it changed concavity. Versus here, it didn't change concavity. So it's not a point of inflection. This is sometimes. Because this is an exception, right? Most of the time when it hits 0, usually it goes from positive to negative. So it's sometimes. It's not never, because obviously points of inflection exist. Does that make sense?
Wait, how would a graph like the y double prime line look?
It would look like, it literally is not noticeable to the human eye. This is exactly the reason why we don't take triple derivatives or anything. It's basically, it goes up, it's concave up, right? If it was 0 for a range, what it would look like, it would look linear, it would look straight, and then it would go back to being concave. That's a bad drawing, hold up. It would be straight, and then it would go back to concave up. But because it's a single point, it's like straight for a single point and then goes back to being concave up. It's not noticeable. Does that make sense? Right? Because
So how would it look like if it wasn't an exception?
if it was like this, positive to negative, it would be concave up and then concave down, like sine. There would be a point of inflection right there, somewhere there.
Got it.
So okay, so that's one. So this is the bulk of your. Did he have these on your pretest?
No.
Okay, this is, I don't know. And on my test last year, this was a pretty decent portion of our points, but I don't know. I have a few more.
Wait, can you send pictures of these if you have any?
Yeah, I can. I mean, we're doing them. I'm gonna be doing them all right now, so you can always refer back to the video. But yeah, I can try. So I can do that. Yeah. If
Will you post the video on the Discord?
yeah, I will do that. I sometimes forget to do it, but because you guys have the theory test soon, I will do it right after this. So see, if a f double prime of x is greater than 0 at x equals c, then f is increasing at x equals c. Always, sometimes, or never.
Is it always because the concavity is up?
Does everyone agree with that?
Um.
Yeah, always.
Okay. Yeah. Let's dissect this. This is good. So
It wasn't. Wait. If it was f prime of x is greater than 0, then f is
yeah.
increasing.
So essentially, increasing, that means what? The slope is positive, right? At the point. Does that make sense? Right?
Oh,
Yeah.
Let's look at this concave up function. Right? This is concave up. Does everyone agree? Right?
Right.
The slopes are increasing, right? As you go across. But over here, the function is not increasing, it's decreasing, because the derivative is negative, the single derivative is negative. So whether it's increasing, so this is concave up. So just because f double prime is positive doesn't mean that f prime is positive. Just like if f prime is less than 0, does that mean f of x is less than 0? No, because I could move it up, right? Like y is equal to negative x plus 2. Look, it's all positive over here, right?
Yep.
So f double prime dictates how the slopes change, not how the actual function change, which is what this is dealing with, f, but how the slopes change. So this is a sometimes, because over here, yeah, it's increasing because there are scenarios where it's concave up and increasing, but there's also scenarios where it's concave up and decreasing. Now, if a function was concave up for long enough, it would eventually become increasing, right? So this is more about like, what if it starts off at a negative slope and then it's concave up? There's a little bit of time where it's decreasing, right? But again, if you go on for long enough, it starts to increase if it's concave up for long enough. Does that make sense?
Yep.
Okay. So that's
Although, Sid, really quickly,
yeah.
I think I made a mistake with what I was trying to explain before, but when you were talking about the positive, right, and the double derivative, the trying to see the positive and negative concavities.
Yeah.
And then I said that about the point of inflection, right? If it was just a single like if it was a single derivative and you had plus and plus next to each other, that point would still be considered as a point of inflection.
Yeah, if it's a single derivative. And the reason for that is if you have a positive slope here and you go to 0 here, your slope has to decrease, right? So it has to be concave down here, right? And then if it goes from 0 to positive, then it has to be concave up. So your concavity has to change for this scenario to be possible in the y prime line, not the y double prime, but the y prime.
Yeah, exactly. Okay, that's what I was trying to. Okay, I suddenly thought it was single prime. Okay.
Okay, so that there's yeah okay, we can't do Riemann sums. He hasn't taught you Riemann sums yet, which is really annoying because that's important. But yeah, let's do
You
this.
also learned that first semester.
Yeah, I think that was one of the last things we learned first. We learned that before actual antiderivatives because it's a whole thing. I think I talked about it on the video with antiderivatives, but actually integrals are not equal to antiderivatives. Like that's not the definition of an integral. The definition of integral is
Area.
well, it's not always area because there's negative. But like it's something else. It's something else, and you actually have to do a whole derivation to prove its antiderivatives. But he just skipped all that for some reason. But it's whatever. Let's do this
I
one.
think it's because he made us do a mini midterm, so we didn't have time.
Yeah, which is kind of a shame. He'll teach it second semester. It's something you have to learn. It's on the AP test. It's the whole nature of integrals. So he'll teach it second semester. So it's not that bad. But so if f of x is an odd function, okay, yeah, let's do this one. This one's good. If f of x is an odd function, then f double prime of x is equal to negative f double prime of negative x for all x where f double prime is defined. I'll draw an example of an odd function here, just so you can look at it visually. Let's say this is f of x. Doesn't matter because this applies to, let's say this is f of x. I guess you can think of it as x cubed.
Is it never?
Does everyone agree with that? Do you want to try explaining why it's never?
Well, I think in pre-calc, I don't know if this is the right way, but when we had sine theta, sine theta or something, it was negative sine theta, and they were equivalent. And for cosine, it was cosine negative theta equaled cosine theta. So I thought because they have negatives both inside, that means they can't be true. So if it was just f negative f double prime of x, then it would probably be always.
Actually, wait. I think if I was talking about an odd function, um, uh,
Let's think about it visually. So here, right? If we're at A,
actually, I think I would agree with. I think I would say always.
okay, let's think of it. Let's stop for a second and think about this visually, right? So if this is point A and our value is B, can you agree that at negative A it'll be negative B, right? Does that make sense?
And yeah,
Mhm.
I think another approach also, like if you take the derivative of a function, like of an odd function, it becomes even, and then take the double derivative of that function, and then becomes odd again.
Yeah, and the reason for that is even though the function is odd, look at the. Let me draw this in different. Let me draw this in different. Look at the slopes of these points. They're the same, right? Does that make sense?
Yes.
So the derivative, and you can actually look at this, right? F prime of x is equal to 3x squared. That's even. So this is odd, but if you take the derivative, it becomes even, right? Now let's look at the way the slopes change, right? Here, it's concave down. Here, it's concave up. The same rate. You can kind of see it visually, right? You know it's concave up, but you can kind of tell it's also the same rate, right? So if it's concave down at negative A and concave up at A, then it's odd, right? With the same rate of concaveness. That's not a word, but you know. So it's actually odd. F double prime of x is 6x. That's odd. So every time you take the derivative, it actually switches each of the terms. Even with a neither, right? Like x cubed plus 8, that's an even term. That's an odd term and that's an even term, right? When you take the derivative, actually, that's a bad example. Let's do 8x squared. That's an odd term and that's an even term, right? If you take the derivative, that even term becomes odd, and then that odd term becomes even, or that even term becomes odd, right? They switch. Each of the terms switch even and oddness, but the overall thing is still neither. They're still neither. So, anyways, that was just an interesting thing. But when you take the derivative of an odd function, it becomes even. When you take the derivative of an even function, it becomes odd, right? Does that make sense?
Yes.
Okay, so if we plug in, if we have f double prime of x, right? So f double prime of a, right? A over here. We're looking at the visual, right? F double prime of a is concave up, right? At some rate. We can call it 2. I don't know. It's probably not 2, but let's say it's 2, right? So so if it's concave up 2, what do you think this is? The negative a. What do you think the concavity is? Actually, we can find the exact concavity right here. A, let's say it's 6a. What do you think it is for negative a?
Negative 6a?
Yeah, so it's the opposite, right? So f of negative a, is this true that when you go to the opposite a, the concavity becomes opposite as well? That is true. So this is actually always. Now, the thing you were talking about with sine x, and the reason that we say sine negative x, the reason that that becomes negative sine x, right?
Mhm.
Just multiply both of these by a negative. Now you get sine x is equal to negative sine negative x. Whoa, that looks the same thing, right? So that's why it's tempting to think of it like, oh, the negative just moves outward, but it's more it's and sometimes I fall prey to that too, but it's also important to know the underlying mechanism, which is if you plug in the negative of your number, you get the opposite value, right? So if you plug in the negative of your number, you get the opposite value, right?
Right. And why do we have the negative in front of the negative f, negative a? Why don't we have the negative in front of the left one?
Just to make the problem more confusing, probably.
Oh, okay.
Or yeah, probably. I mean, to me personally, I think this is more readable. This is more useful because when you use the identity, you're usually using it on a single term. But this to me is more readable because it says sine of x is equal to the negative of the opposite value. So this to me looks more readable, and so honestly, I kind of like this better. But if you were to, so this is more of like a special case, and this is just semantics. I'm just talking about notation because we like to write things certain ways. The reason people don't use the same notation for sine x is because usually you have a whole bunch of terms, right? Cosine x times 2 sine x plus sine negative x, and you're just applying it to a single value. So it's easy to just remember, hey, the negative moves outward. It's just an easy way to remember implicitly through the notation. We're kind of describing it that way. Okay, so that's all the ones I have. So I don't really have any more good ones. Do you guys remember how to do E? Like am I okay with erasing this? I don't know. I don't know if you guys are writing this down, but you don't need to. But if anyone is, can I erase this?
But could you briefly just recap that?
Yes. Okay. So essentially, we were talking about how when you take the derivative of an odd function, it becomes even. So it switches even and odd every time you take a derivative.
Mm-hmm.
And that actually it's the same thing for neither as well. It just happens with each of the terms. You can see each of the terms change even and oddness, even though the whole function stays neither. So, we were just saying, okay, if we have this statement, is it always, sometimes, or never? Well, if you have f of x odd, f double prime, f prime is even, so f double prime is also odd. So when you plug in the negative value, you should get the opposite y value as well. So this is true. Does that was basically a recap of what we did.
Wait, what? Could you repeat the last sentence?
Okay, so in an odd function, which is f double prime, right? If you plug in, you have a over here, right? If you plug in negative a, you'll get the opposite value, right?
Oh yeah.
And this can be seen visually in the concavity, right? You have the exact opposite concavity. I just made an example odd function x cubed, right? You have the exact opposite concavity at a and negative a.
Uh-huh. Okay, take it.
Okay, so that was okay. So that's that. Okay, yeah, that should be most of it. Did you guys do the derivation for the Pythagorean theorem? Probably not.
No.
Okay, yeah, that's fine. I'm just looking. You guys didn't do delta epsilon proofs, right? If you don't know what that is, then you didn't do it, right?
No, we didn't do it.
Okay then.
Do we have like a list of derivations that we need to know?
Yeah. Did he give you a list?
He didn't.
Oh, okay. I mean, from what I can tell, it seems you guys, so you need to know how to derive all the trig functions with the limit definition,
Mhm.
you need to know sine x over x using the squeeze theorem. So, drawing the three,
Okay.
do you remember that?
Yeah.
Yeah, so you need to do that. And then you need to also do, this one I don't remember, but it's also one you should know, C in terms of F,
Oh, G in terms of F?
or C in terms of F.
Celsius.
Yeah,
Got it.
sorry. Celsius in terms of Fahrenheit. And then, I don't know, you guys did integration by parts, right?
Like
Oh,
separation?
we're doing a BC. Yeah.
Wait, did you guys do integration by parts? I feel like like,
No, he said that we're gonna do it in BC.
whoa, what? Damn. Okay, we did that in AB. I don't know why.
Wait, what?
Yeah, I
What?
mean, it's
What?
it's not that big of a deal. It's honestly pretty easy, but okay, so
Oh.
ignore that. Do you guys do you know how to do the derivative of x to the n by limits? So finding f prime of x, f prime.
Binomial expansion.
Yeah, it's binomial expansion. Does anyone need that done?
Yeah, could you do that real quick?
Yeah, okay. This one's pretty, I like this one. This one's pretty awesome. So f prime of x is equal to the limit as h goes to 0 of x. I'm just gonna skip ahead a little bit, and I'm gonna say x plus h to the n minus x to the n all over h, right? That makes sense?
Yeah.
Also, that's something you need to derive visually, right? The limit definition of a derivative. But anyways, so if you remember from pre-calc, we learned binomial expansion, so we can actually expand this out in terms of combinations. So that's combination n0 x to the n h to the 0 plus combination n1 x to the n minus 1 h to the 1. Do you guys see the pattern?
Yep.
Okay, so we go all the way to combination n, choose n, x to the 0, h to the n, right? Minus x to the n all over h. Are there any terms we can cancel out? There's one. It's kind of hiding because there's a lot of notation, but what's
The
n?
first and last one?
Yeah, what's n choose 0? That's just if you have n objects, choose 0 of them. There's only one possible outcome, so that's 1. So that's gone, and that's gone. So now we can actually, all of our terms have h in them. The ones inside and the ones out here, they all have h, right? So we can actually divide by h now. So now we get the limit as h goes to 0 of n choose 1, x to the n minus 1, x to the n minus 1 plus n choose 2. I'm just going to expand it out a little bit more. X to the n minus 2, h to the 1, because we divided by an h. And we go all the way to, sorry, this is getting cramped. Let me. So then we go all the way to n choose n, x to the n minus, x to the 0, h to the n minus 1. What's the limit of that as h goes to 0?
And x to the n minus 1.
Yeah, because all these terms drop out because they have an h in them, so it's just n choose 1 is n, so that's n to the x, n minus 1. So that's f prime of x. So that's that derivation. Okay. What else do you guys need to know? I'm just looking. Do you guys know how to do the derivative of ln x by limits and log x by limits?
Yep.
Okay. Do you guys do e to the x by limits? I don't even know if we did.
Can you repeat what you said?
E to the x by limits, the derivative of e to the x by limits.
We might
No,
have.
not by limits. Not by limits.
Okay then. Ignore that then.
What did we do?
Wait,
And it's yeah. Never mind then. I don't even think you derive it, because actually the definition for e, people say it's the natural number because it shows up in nature, but it's actually literally the function that's derivatives equals itself. That was literally the definition for e. So that's why That's why you don't really drive it. But or did you guys
Could
drive it?
you-
Not by limit, but there might have been another way you guys probably derived it.
Yeah, wait, to the LN way.
Yeah, the ln way. Yeah.
Wait, could you like explain like domain of like inverse trig functions?
I could. We talked about it for like 30 minutes in the beginning. I'm gonna upload it if you want. If it's
Oh,
okay,
okay,
could you?
okay,
Yeah.
okay.
I explained it in detail. There was a little bit of waffling in the beginning, but if you skip to maybe, I don't know, 20 minutes in, I actually give like a full proper explanation of everything. So
Okay, thank you.
okay. Newton's approximation. Do you guys know how to do that one?
Yes.
Okay.
Yeah.
Then it's derivative inverse function. If you need help on that, check the video that will be up soon. Shoot.
Wait, Newton's approximation is like what, like x0 minus f of x0 over f prime x0, or f1 x1.
Shoot. Sorry. What were you saying? Let me erase it.
Oh, like what's the thing for Newton's approximation again? Like I know like the derivation, but like I just forgot the end product.
I forgot it too. I just derive it every time. I'm gonna be honest with you.
Okay,
Yeah. Just make sure he gets really angry about this. Like every year he talks about someone who did this. Make sure when you draw your visual, oops, that's terrible. If that's even worse. If you draw your function, make sure it actually hits the x-axis, because that's the whole point of Newton's derivation, is that you get closer and closer to the whatever hits the x-axis, right? This makes no sense. You're not approximating anything. You'll just go to, if you every time you find another x1, right? You'll just go to infinity. You're not approximating anything, right?
yeah.
So make sure it actually hits the x-axis. Okay. There was something sent in homework help. Do you guys need that?
Oh yeah, I just said that. If we have time, can we do number 9 and 10?
Yeah, let's do 9 first. Okay, 9. Consider the curve given by, okay, so let me write that curve. X squared y minus 4x plus y squared is equal to 2. Find the equation of the tangent lines at each of the 2 points on the curve where the x coordinate is 1. So tangent line, I'm going to underline S at x equals 1. Okay, well, what does this look like? Actually, instead of doing that, I'm just going to take the derivative. So at x equals 1, I'm assuming that this is a function of y in terms of x, right? Actually, it doesn't even matter. But what I want to do is to find a tangent line in the xy plane, I need dy dx, right? So I need to take the derivative of y with respect to x. Let's implicitly differentiate this, which is just a chain rule. If you want more information on that, watch the video I made on implicit and absolute differentiation. It's really helpful. I think whoever was there for that lecture, I don't know. I thought it was pretty helpful because I explained things pretty well. But
Yeah, I'll go check that out then.
oh, well, what'd you say?
Oh yeah, I just said yeah, I'll go check that out.
Yeah. Okay. So we take the derivative, product rule, f prime times dx over dx, right? But that cancels out. So f prime of g plus g prime of f minus minus the derivative of that plus 2y times dy dx is equal to 0. Derivative constant is 0. So if we have x equals 1, we also need a y. So let's actually plug this into our original function and see what y we get. So y minus 4 plus y squared is equal to 2. So y squared plus y is equal to 6. Let me put that actually back there. Y squared plus y minus 6 is equal to 0. Y plus 3 times y minus 2. So that's why he says tangent lines, because there's actually 2 y values. So there's 2 tangent lines. So we have to find the tangent line at point 1 comma negative 3 and 1 comma 2. So let's do that. So let's do the first one. I'm going to do this one first. I plug in 1 comma negative 3. I get negative 6 plus dy dx minus 4 plus 2y. What's 2 times negative 6? Well, negative 6, so minus 6 times dy dx is equal to 0. So that's 5 dy dx is equal to negative 10. So dy dx is equal to negative 2. So that's, and so we have a slope, we have a point, we can do point slope. So y plus 3 is equal to negative 2 times x minus 1. You can expand it out if you want. I'm just going to leave it like that for now. I'm going to erase this just for space. I think that part's pretty easy. Oh, I just erased the derivative. Let me do that. 0. Okay, so now we need to do this point. So 1 comma 2. So that's 4 plus x squared. So dy dx minus 4, so yeah, that's just a constant, plus 2y, 4 dy dx is equal to 0. I'm going to keep the dy dx's on this side just because they're positive already. Oh, and those cancel out, so it's just 0. So dy dx is actually equal to 0 there, I think. So that is y is equal to the y value here, 2. That's the slope of 0. So those are your 2 answers, I think. I'm not sure though.
I think you're correct.
Yeah, that's right.
Okay, and number 10. Okay, yeah, let's do that one. Number 10.
Could you just briefly explain 7 afterwards?
On the same picture.
Yeah.
Yeah, let's do that. That one looks cool too. Let's do this one first, and then I'll go to that one. So, if g of 2 is equal to 5, and g prime of x is equal to 10x over 9 minus x squared, then estimate g of 2.2. So estimate g of 2.2. Okay, well, we know g of 2 is equal to 5, right? And we know that g prime of x is equal to this. Now here's the thing. So we have a point 2 comma 5, right? And the slope of that point, right? We have some curve. I'm not sure what it looks like. Let's just pretend it looks like this. It honestly doesn't matter, right? It could be the other way. It could be whatever. And the tangent line looks like this, right? To approximate, local linearization is essentially saying, let's go out on that tangent line to approximate instead of actually plugging in the point, right? So if we already know that this is 2 comma 5, let's just find the slope at 2 and then do that approximation. So the slope at 2 is 20 over 9 minus 4, so 5, right? G prime of 2. So that's equal to 4. So that's our slope, right? And how far away, so a slope is just rise over run, right? So for every, I guess we could set it up like this, right? For every one change in x on the bottom, we get 4 in the change in the y. And we know that the distance, or the change in x over here, is 0.2, right? And this is just a shortcut. You could make a tangent line out of this and then plug it in that way, but this is, I like this better. It's not really a shortcut because you're still like doing it conceptually, so I like it that way. But anyways, so the change in x is 0.2, right? So that means for a change, instead of a change in x of 1, for a change of x of 0.2, what's our change in y? I'll put y there just for consistency. So 4 times 0.2, that's 4 times 2 over 10. So that's 8 over 10. So 0.8 is equal to y. So we just take, so that's our change in y, right? So let's just add that. And again, this is just an approximation, right? So let's add that to our y value. So it's 5.8. That's our answer. Does that make sense? All those steps? Right? This has a slope of 4. But we went out 0.2.
4 is equal to y over 0.2.
Oh, this was just a little inequality I set up because we know our change in 2 is, we know that we have the slope of our, do you agree that the slope of our point is 4, right?
Yeah.
So that means for every 1 we go out on the x, we go up 4 on the y, right?
Yeah.
So if we go out 0.2 on the x, which is how much we're going out, right? Over here, that's how much we're going out compared to our original point, right? I'm basically making this inequality to say how much are we going out on the y.
Oh, so you're basically doing changing x and changing y
Yeah,
because it's rise over run.
yeah,
Oh, that makes sense.
yeah. And it's just, I mean, you could also just say 4 times 0.2, right? Because you're taking 0.2, or you're taking basically 0.2 of that 4. But anyways, yeah. So I set that inequality. Does that make sense, Derek? Again, this is basically just
Yeah.
a shortcut. What he wants you to do is make the line, right? So y minus 5 is equal to 4 times x minus 2, and then plug in 2.2. But like, I personally think this is kind of this is the kind of shortcut that's not like impeding on your understanding, because you actually have to understand what you're doing with local linearization to realize why this makes sense. So I think it's a valid shortcut. So, yeah. And then number 7. Does that make sense? Actually, before I erase it, what I did.
Yeah.
Okay, cool. Let me do number 7. Number 7. Okay. Limit as h goes to 0 of tangent pi over 4 plus h minus tangent pi over 4 over h. So let's look at this. Let's do kind of a reverse and look at this visually, right? We have tangent x. I think it looks like this, right? And that's pi over 2, negative pi over 2, right? And we have tangent pi over 4, right? Pi over 4, what's the value of that? 1? I think it's 1, yeah. And we have another point. That's pi over 4 plus h, and that is tangent pi over 4 plus h. What's the slope between these 2 points? Sorry, if I had drawn this better, I would have made it look more like that. But what's the slope between these 2 points?
Tangent pi over 4 plus h minus tangent pi over 4 divided by h.
Yeah, divided by x plus h minus h. It's just point slope. Y1 minus y2 over x1 minus x2, right? So, I don't know. That was just a long-winded, like, visual way of showing you that this is just the limit definition, right? F of x plus h minus f of x over h, right? As this point gets closer to this point does not move at all, right? That's why we're taking the derivative of this point, right? So as this point gets infinitely closer to that point and we're taking the slope of it, we're essentially getting the slope of this point. So that's the derivative at, so if f of x is equal to tangent x, that would be the derivative at x is equal to pi over 4. Does that make sense? I tried explaining that as visually as possible because it's a cool theory thing. So I mean, it's not necessarily theory, but it's like, you know, you're visualizing it, so that's kind of cool. So that's that is secant squared, right? Secant squared x 1 over cosine pi over 4. So 2, I think, because it's root 2. Shoot, yeah, root 2
that's
squared.
right.
Yeah, root 2
Yeah,
squared.
2 is the right answer.
Okay, so that's that. Does that make sense? Is there any questions about that?
No.
Okay.
Well, it makes sense.
Okay. Someone said do 11 on the theory worksheet. Is that the one in homework help? Oh, yeah, it's this one. Okay. What is the greatest rate of increase of the function? Okay, this is cool. I like this one. So you guys are probably familiar after critical numbers and having to retake it, right? Of the greatest point on a function, right? How do we find the greatest point on a function?
You take a derivative and then
Y prime.
move it to maximum or minimum.
Yeah, so you take the derivative. yeah. So you take it the derivative, set it equal to 0, find all those points because one of those has to be your absolute maximum unless there is none and it goes infinitely upward, right? And then you find your absolute maximum. So if we want to find the maximum, because essentially what this is asking is the maximum rate of change. Oh wait, no, this is the maximum rate of increase. Yeah, that's the same thing actually. The maximum rate of increase is the maximum rate of change on the positive. It's maximum because it's the greatest rate of increase. If it was asking for the greatest rate of decrease, that would actually be the minimum slope that you have in your function, right? The lowest slope you have. So to find the lowest, but we're finding the greatest rate of increase, so we want to find the maximum slope on our function. So to find the maximum slope, we need our slope function. What's our slope function? The derivative of f of x. So f prime of x is our slope function, right? And we'll say 3x squared plus 6x. So that's we're actually finding the maximum of the derivative, not the original function. So let's take f double
You have
prime.
double
It's
prime then?
negative. It's negative 3x squared, right?
Oh, is it? Oh shoot, that
Yeah,
is a
the
negative.
negative x
Bruh,
cubed.
it blended into the equal sign.
Wait, so
Okay.
don't we just have to find f double prime?
Yeah. So to find the maximum, to find the maximum f prime, you take f double prime, which is negative 6x plus 6. Find the in this case our critical number, right? Because so this is actually our y prime line. You can think of it as our y prime line, right? And we're finding our critical number, set that equal to 0. We get -1, goes from positive to negative. So that's, and this is not what our graph looks like, but this is what the graph of our derivative looks like. I just want to point that out, right? So that's our maximum slope right there at -1.
That's wrong. That's wrong though.
That's the x value. That's the x value.
Yeah,
You need to
yeah,
find the
don't-
greatest.
don't-
Now you need to
yeah.
actually find the rate of
Yeah.
increase, the greatest rate of increase. So you have to plug it back into f prime of x, right? You actually have to find the value of this, right? If it's like 1 or 2 or 5, you actually have to find the value because it's asking for that rate, not the x value of the greatest rate of increase. Does that make sense? So if we plug this back into -1,
Oh,
we got -3 minus 6. So -9,
Which is
which is
wait,
funny.
no, we get
Negative,
three. We
negative
get
3
three.
plus 6.
Hold up. But isn't it -1?
It's negative
It's
3 plus
positive
6.
1.
It's positive
Because it's
1.
squared.
Oh, bro.
Wait, did he ever give you guys an answer key for that paper?
Oh yeah, he did. It's posted on Google Classroom. The answer is 3.
Yeah,
Oh,
it's -3 plus 6. Yep. Cool. Okay, so
I
that's
actually also.
Wait,
yeah.
that's the the line that you drew is a y double prime.
Yes, this line is not y prime. Let me not. I mean, it's not f of x. It's f prime of x. Because I mean, I'm just having a little fun because it's like we're basically finding the critical numbers of the derivative and not the original function, and that's kind of rare. So
Isn't that the prime line for f double prime x? F prime x.
shoot, am I tripping? No, it is f prime of x actually because
Wait, how come?
It's,
I mean, okay, I can
It looks like it's double prime.
It is double prime.
I can show you this in multiple ways. One, this is a quadratic and that's a quadratic. That's like the most blunt proof I can show for that. But let me. It's also because the way I drew this is positive, right? So I'm drawing a graph with slopes that are positive, and then graphs with slopes that are negative. That's why this is the y. I'm kind of just like freehanding the y prime line based on, or I'm freehanding this graph based on the information, right? Positive slope starts positive, then it goes to negative, so it has to look like that. Does that make sense? Am I saying something wrong? I might be, but that's f prime.
Yes, basically, what you did was the double prime line. You just drew because you factored the -1 from the double prime.
Yeah, so this is actually
Double prime.
f double prime of x. I called it the y prime
Right.
line because we're finding the critical numbers of this. It was just a little like I was just having fun because that's basically what we're doing. But this is actually
Oh, I
the
see.
double prime. Does that make sense?
I think we were just confused when we saw the Y
Yeah,
prime.
yeah,
That
yeah,
we
yeah.
couldn't
Sorry.
notice.
Yeah, I could put it like that. I mean, yeah. I don't know. It's debatable whether this is a Y prime or Y double prime because the way I'm
It's y
drawing
prime
it is,
of y prime.
yeah, it's the Y prime of Y prime. So I don't know. It's debatable, but yeah. So that's
Oh, well, in that sense, it makes sense.
yeah. So okay, that should be mostly everything. I'm looking. Did you guys do Noon's cooling? I think you guys did. That was. Do you know how to
Yeah,
derive
yeah,
that?
but he said it's not on the final.
Oh, really? Yeah. Okay.
No,
That
No,
was,
no, no. He said it's gonna be
Well, it's
on
not
the
on.
red.
Well, it's not on theory. It's not on theory final.
oh, okay.
Seriously?
Oh, this one's actually cool. Hold up.
Yeah.
This is actually a problem that even like I couldn't even do. Like I was actually messed up after seeing this problem. So it is the limit as x goes to 0 of 1 minus cosine x over x squared. But here's a catch: x is in degrees. It's actually kind of crazy. So what do you think? So the reason that this is important, and I'll let you guys think about it a little bit before I show the answer, but the reason that this is important is because cosine is in radians. It's always in radians. Even when you guys are in this beginning of pre-calc and you say, what's cosine of 30? That's just you doing it in your heads. In the calculator, cosine is always in radians. Even in degree mode, it's still in radians, but instead of using cosine, they say cosine of 180 over pi x. Whatever you plug in the calculator, it goes through this. Cosine is inherently always in radians. So that's why so if cosine is always in radians, how are we going to make it so that it agrees with being plugged in a degree value? That's the heart of this problem. So, I don't know.
X times pi over 180.
Yes. Do we
over 5?
so we do 180 over pi in here. Do we do it in here as well?
No.
No, because we
Wait.
don't. No,
Yeah,
because
no.
we don't need to.
Because it's
Oh, do you want to explain?
no, I think it's just in terms of cosine because they're saying cosine because x is in degrees. It's like for the trig function.
The reason we only put so the first step to this is 180 over pi x over x squared. The reason we don't put 180 over pi over here is because the only reason we need 180 over pi in the first place is because cosine takes only radians. So we just need to adjust this to take radians. That's all. We don't need to adjust this. This is still an x squared. So this is still an x squared, and we don't need to adjust this at all. Does that make sense?
Yeah.
So
But,
now,
but then
oh,
why is only pi like needs to be in radians and not like sine or like tangent?
tangent also needs to be in radians, and sine also needs to be in radians. All the trig functions are in
Any
radians.
trig function.
Even cosine, all of them. When you do when
So
when
if
you,
x,
keep going.
yeah, so if x is 30 degrees, then you would convert the 30 degrees into radians, but you'd put 30 squared instead of
Yeah.
whatever in. Okay.
Yes, and the reason for that is if we put 180 over pi in here, it's a different problem, right? Right? Instead of being over 30, now it's over some other number, and that's not what we're doing. The only reason we have 180 over pi here is because cosine takes only radians. It doesn't take degrees. Even though in your head you might say, okay, cosine 30, it only takes radians. That's just the way the way cosine has been set up. And it's also because when we did the derivative of cosine, we assumed it was in radians, right? when we did the derivative, when we did squeeze theorem as well, right? We assumed it was in radians. So everything about derivatives and limits and calculus was built on the fact that our trig functions were radians. So that's why we have to only convert this into radians in here. It's still a bit weird to me, but that's the reason.
But then how do you progress from there?
From there, then you just take it. Then you just do the limit normally. So there are two ways you could go about this. One is to use. Did you guys learn L'Hopital, the hospital?
No.
Okay. So the way you would do this is 1 plus cosine pi or not pi over 180.
Mm-hmm.
180 over pi x, and then do that to the bottom as well. And so you get 1 minus cosine squared, which is sine squared. 180 over pi x over x squared times, I'll just put blah 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 in here still, right? We have a 180 over pi in here, but we need it out here, so let's put 180 over pi squared because we want to do this twice, and then let's put that over here as well. Oops.
Wait,
And then
pi over 180, is that 180 over pi?
oh, is it? Yeah, it is actually. Wait, hold up. I think in here, is it supposed to be? Yeah, it's pi over 180. Whoops. Okay, so that's pi over 180. Actually, no.
Wait, what? It's 180 over pi, right? Because it's radius to degrees.
Yeah, it is 180 over pi. Because
What?
if x is to 360, like actually that's a bad way to say it. If 180 is, shoot, how do I do this? It's, how do I explain this? If x over this is in degrees, right? X is in degrees, is equal to, damn, how do I do this? Well, okay, imagine you're
Does it say
plugging,
like?
if you're plugging in, actually, no, he is, wait, is he right about this? I think it is.
Wait.
It is, because
Alright.
it is pi over 180,
Yeah,
because
it
if
is
you
pi
plug in
over
180 over x, yeah, hold up, yeah, that makes more sense. Sorry, yep, that is pi over 180, that's pi over 180, pi over 180. So now this goes to 1, so it's pi over 180 squared over, what was it? 1 plus cosine 180 over pi. Right, and then you can actually plug in the limit now. X goes to 0, that becomes 2, so it's pi squared over 180 squared times 2.
Do you have an x squared on the bottom as well?
That went away, remember? We did sine squared.
Wait, how do you have the pi over 180 if you don't convert the radians in the denominator?
I put it there, and then I compensated by putting it on the top as well, right? If 2
Oh,
over
yeah.
3 times 2 on the top and times 2 on the bottom, you know?
Yeah.
Okay, so that should be everything.
Oh, okay.
Does that make sense? This is probably
Yeah.
not. It's probably not going to be on your theory final, but it's a good thing to know that the difference between radians and degrees. Okay. That should be everything. You guys know IVT.
Wait, did
Where's
you
the
go?
answer?
Oh, right here. It's not like multiplied out or anything because I don't want to do it by hand, but it's 180. It's pi squared over 180 squared times 2. Does it make sense how I got
Where
there?
did 2 come from?
If you plug in as x goes to 0, 1 plus cosine 0. So it's 2, 1 plus 1. Because it's still here. I put dot 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 here because I multiply on the top and bottom and I didn't want to write again.
Wait, when you compensated, you did pi over 180 times x to the power of 2, right?
So I had sine squared pi over 180 x squared, right? And then because over here, because I multiplied it over here, I also have 1 plus cosine pi over 180 x, right? Does that make sense? Does that make sense for everyone?
Yeah.
Yeah.
Okay. Oh, did someone say no? I didn't hear.
So everyone said yes.
Okay.
Yeah,
So
we said yes.
okay, so pi over 180. I have two signs, right? This is basically sine pi over 180 x times sine pi over 180 x. So if I want to cancel each of these out, I need two pi over 180s, right? So I multiply by pi over 180 squared, right? So now I can split this into pi over 180x and pi over 180x, right? Makes sense? But since I put that down
Yes.
here, I need to compensate by putting it up here as well. That's all. And now I can cancel these out and this out. And so now I'm left with pi over 180 squared. And the reason I can cancel them out is because squeeze theorem, since we're doing it in radians. If we were doing this in degrees, I'd have to rederive squeeze theorem in terms of degrees. So, and then you could technically rederive everything in terms of degrees and do it just for this one problem, but you don't have to. You could just put it in radians. So pi over 180 squared and all over 1 plus cosine pi over 180x, right? Limit as x goes to 0. So, you know, you plug in x equals 0 now that you can. So that's 1 plus cosine 0. So that's 2 on the bottom. So it's pi over 180 squared over 2, which is equal to that. Does that make sense?
Yeah.
Okay. Because all I did was move it inside. I distributed the squared and then moved it. Okay. So that should be everything. Is there any more questions? I can do maybe one more.
Yeah, I had a question about limits that axis approaches infinity.
Yeah.
When can you cross out constants?
Could you give me an example?
I had like x squared plus 10 over x squared.
X
Like you
squared.
cross out the 10 and we go to 1, right?
So x squared over 10 plus x squared. So x squared over x squared plus 10, basically, right?
Yeah.
So if these have the same power, then it goes to infinity at the same. Oh wait, no. So limit as x goes to infinity, right? Is that what you're saying?
Isn't it just one?
Yeah, it's just 1.
Yeah.
Yeah. So 1. So what's the question here?
So when can you like cross out constants to make it equal to 1?
So to cross out constants, like if there's a 2 here, is that what you mean? Oh, when can you take these away? Is that what you're saying?
Could you cross out the 10? Yeah.
So if these are equal powers, they grow at an equal rate, right? So you can disregard everything else because at infinity, these leading powers are going to be so huge, everything else doesn't matter. Now, if this is bigger than this, so like x cubed plus 3x plus 10 over x squared plus 3, I actually don't know a good example. You would, since this is growing faster, it's going to infinity, right? But since this is bigger and it's being divided by something, it's going to infinity. We want to know at what rate it's going to infinity to, right? So we can actually do long division. Do you guys remember this? Do long division. I'm not doing it, and I don't even know if it's possible to do long division for this problem. But you do long division, and you'd figure out your remainder. You would get like, oh shoot, what would you get? You would get like, hold up, give me a second to think about it. You get like x plus 2 plus some remainder, like 3 over, shoot, what is it? X squared plus 3. And as this goes to infinity, it becomes the line x plus 2. Actually, that's bad. It becomes the line. It's a whole thing. This wasn't a good example, but do you guys remember doing that at all?
Yeah.
Okay, so that's a whole thing. So that's when you don't cross out constants. And then if it's on the bottom, it's bigger, then it just goes to 0. You don't care. So it's only when you only cross out constants when they're equal powers. right? Or when it's even for this, you can't cross out constants, right? Shoot, x minus x squared plus 10. You don't cross out constants here. You know that, right? This is probably on the theory final, or at least on the operations, right? Limit as x goes to infinity.
You multiply by the reciprocal, right?
Yeah,
Oh,
by
yeah,
the
like-
the conjugate.
the
Actually, it's not even called the
yeah.
conjugate. The conjugate only applies to imaginary numbers, but you can call it the conjugate. Everyone calls it the conjugate. So yeah, you multiply by the conjugate. So this is a special scenario. Honestly, I'm not even sure why it matters here. So I just do it because it's a special scenario. Can I go over graphings with limits? Like this? Is that what we're talking about? The person that put that in the chat. Okay, they might be out right now. Oh, okay. Yeah, there. So, I wish I had a good example for this, but when you come across it, just divide and you'll see what I mean. So, anyways, that should be everything, I think, about graphing with limits. Is there any other questions?
Wait, so that top one would be infinity, like the last one you did, the x.
This one up
third
here?
plus two.
This one?
Yeah.
You would have to multiply by x plus this, so you get x minus x squared plus 10 over x plus square root x squared plus 10, right? Oh, and then you would get
No, wait. I was talking about the x third plus 3x plus 10 over x squared plus 3.
this one. Once you divide it out, you usually get a line and then a constant that as you go to infinity, goes to 0. So then you start following the line, right? So this would be the asymptotic, the slant asymptote. Let me search up an example really quick. This
If we had to take the limit of that question, would it just be infinity?
yeah. This is just for
Graphing. Okay.
let me find one. Yeah, so see how he crosses out and then you get negative 2x plus 9 over 6 over x minus 2, or negative x plus 2, right? As this goes to infinity, that remainder, that really complicated part at the end, goes to 0, right? So then your function starts following the line, so that becomes your slant asymptote. If it's a plus, then that means it's going over the line, so it's approaching the line from the top, like it is over here at the left side of this graph. But if it's a minus, then it's coming from under the line, like it is over here.
Wait, if what is minus and what is
If it's negative 2x minus 9 minus 6 over negative x plus 2, so if that really complicated term is being subtracted, right? Does that make sense?
So if it's being
If it's being subtracted, then what?
If it's being subtracted, then that means it's coming from underneath, right? Your graph, since technically that value still exists, right? Even if it's really small, right? So you're right under the slant asymptote, so it's over here, like on the right of this graph. You see how the graph is coming from under the asymptote, right? Instead of over. It's because in that case, it's a minus instead of a plus over here.
Oh, so if it's a plus, it could like be above the tangent line.
Yeah,
Or
like
whatever the
like
basic
over here,
difference.
like over here. It comes from above. Make sense? That's probably something you don't need to know because you'll have enough other information to just guess anyways. But I don't know, it's just something you can think about.
So would the theory funnel have any graphing on it?
Probably not. That was just, I don't know, a tangent, I guess.
Probably it might have like a question like number 84.
Oh, I see that one.
Okay. I have to go eat dinner because I haven't eaten dinner yet. So I think that's enough. I think that's enough for today. I think that should equip you with everything you need for the theory. Those of you who weren't here for the sometimes, always, never questions, you probably want to watch the recording and look at that. But yeah, that's the bulk of. So go watch that because go watch that in the archived recording because that's the bulk of your theory final. But other than that, you should be good.
Was
Alright.
it on this one?
Yeah,
Or
yeah,
the
this
one
theory
thing?
final. Yeah,
Oh yeah.
you'll see when I'm gonna upload the archive right now. So, all right.